Okay, this next video we're gonna talk about some log properties, and understanding these log properties is very helpful in understanding logs. So what I'm going to do here is I'm going to give you on the left, I'm going to give you a property of a log, and on the right I'm going to give you an example. So the first log property says that if you take the log of some argument, say a, using the same base a, that's always going to equal to 1. Now on these first couple I'm going to show you why, but on the rest of them I'm not going to, because it takes a little too much know-how. So here, if you converted this equation to exponential form, you would say a to the 1 equals a. And so you can see that that's a true form in exponential form, so therefore it must be true in log form. And an example of this would be like if you said the log of 7 base 7, well, that would have to be 1, because you have a base here, an argument of 7, and the base is the same. Let me show you a couple of other examples that you might not readily identify. The natural log of e would also be 1, because remember, it's understood that the base of natural log is base e. So you have an argument e and a base e. The common log of 10 would be 1, because remember, it's understood that the common log has base 10. So here you're taking the log of 10 with the same base 10, so that would equal 1 as well. Now the next property says that the log of 1, any base, is 0. And that's because if you take any number a and raise it to the 0, you get 1. So the log of 1, no matter what the base is always going to be 0. So, and even if you said the natural log of 1, you get 0, or the common log of 1 would also be 0. Also, the next one says if you take the log of a to the p, where this is a base a in this exponential, a to the p, and if the base is the same here and here, then this log is just going to equal the power p. And you can see what would happen if you converted this to exponential form. You would have a to the p equals the argument a to the p, which of course is a true statement. So we know that this is a true property. So if you had the log of 8 to the third base 8, you could say that's just going to equal 3, because the base here is 8 and the base here is 8, so it's going to equal 3. Now if you had the common log of 10 to the x, well, you know that this is understood to be base 10. So you have a base of 10 here, base of 10 here, so the result has to be this power 2x. Or if you did the natural log, well, again, you know the natural log is base e, so here you have a base e and here you have a base e, so this would have to equal the power x plus 1. Okay, the next property is the log of a product. The log of a product of two values, so the log of m times n, is equal to the sum of the two logs. And of course, on all of these you have to keep the same bases on these next few properties, but it would be the log of m base a plus the log of n base a. So this is helpful in solving equations, and you can go both directions. If you had the log of xz base 3, you could write that as the log of x base 3 plus the log of z base 3. But you could also go the other direction. If you had these two, this sum, you could write it as the log of x times z. Okay, for a quotient it works similarly, but the log of a quotient is actually the difference of the logs. So if you have the log of m over n, then that would be the log of m minus the log of n. So for instance, if you had the log of x over y base 3, that would be the log of x base 3 minus the log of y base 3. Or again, you could go the other way. If you had log of x base 3 minus log of y base 3, you could actually write it as a single log, log of x over y. Now number 6 here might look a little bit like number 3, but notice the difference. In number 3, these two bases were the same, but in this one it's a different base. So a and m are not the same bases. So what we have to do there is a property we can use, but we end up saying that the log of m to the p is actually p times the log of m. So let me show you how that works. See, notice here the difference between this example and this example up here is, in this example up here I had 8 for the base in my argument and I had 8 for the base with my log. Well, here I have 5 for the base in my argument but 2 for the base in the log, so these two bases don't match up. Remember, if they matched up you would simply get the power, but that doesn't apply here. So what I have to do, the only thing I can do here is just take this 3 and I can write it as a factor, 3 times the log of 5 base 2. And then if I have this, I have a base 7 here and a base 4 here, so I can't just eliminate the log, but what I can do is write this as 2x times the log of 7 base 4. And now these next two properties have to do with the one-to-oneness of logs. So if two logs are equal, then their arguments must be equal. So if log of m equals log of n, then m must equal n. And this can be helpful in solving equations. So if you have the log of 2x plus 1 base 10 equal the log of 6 base 10, then you can drop the logs and say 2x plus 1 equals 6. And likewise, you can go the other way. If m equals n, then the log of m base, any base, is equal to the log of n, same base. So if I have 3 to the x equal 25, then I know if I wanted to, I could write that as log of 3 to the x and use whatever base I like, equal to the log of 25, again using whatever base I like. And then this last property, a little hard to see because the exponent here, but a to the log of p base a, so this is the log and the argument is p and a is the base. So if you're taking a base a and raising it to a log that has the same base, then the result is simply the argument of the log, p. So over here I'm taking a base 9 and I'm raising it to a log base 9, so the result is simply the argument 5x. Here I'm taking e and I'm raising it to a log base e. Remember, natural log is a base e log, and so the result is simply the argument 3x. And then here I'm taking 10 and I'm raising it to a log base 10, and so the result is just the argument of that log, which is 8. Now, these next couple of examples are just practice for you to do the log properties. So what you generally are asked to do, you're asked to either, given a log and asked to write it as a combination of logs, or you're asked to go the other way. You're given a combination of logs and asked to write it as a single log. So this time we're given a single log and we're asked to write it as a combination of logs. Well, the first thing I want to do when solving this, I want to go ahead and write this square root of z as a power. So I'll write that as z to the 1/2. Now, the property, this is a quotient. So this is m and this is n. And so we have a property up here that says that if I have the log of m over n, I can write that as log of m minus log of n. So I can write this as the log of the top minus the log of the bottom. Now, here I have a product. I have m times n here. So up here I have a property that says if I have the log of m times n, that's the log of m plus log of n. So I can break this up as log of x squared plus log of y cubed. So I break that up like that. And I just brought the third term down. Now, each of these has a power. This is log of x squared, this is log of y cubed, this is log of z to the 1/2. Well, there's a property number 6 says if I have log of something to a power, I can write that as the power times the log. So I can write this as 2 times the log of x base 3. I can bring the 3 down here and write this as 3 times the log of y base 3. And then I can bring the 1/2 down and write this as minus 1/2 the log of z base 3. Now if I go the other way, like if I have an expression like this, I can write it as a single log. So if I have 1/3 log of x, if you go back up there and look at that property, well, you remember you can take this 1/3 and you can move it back as an exponent. You can take this 2 and you can move it back as an exponent. And you can take this 3 and you can move it back as an exponent. So this would be the same as saying log of x to the 1/3 power. This would be log of y squared. This is common log, so I don't have the base written. And then log of z cubed. Now, since I have a sum, these two represent a sum, so I can rewrite this as a single log as the log of a product. So I would write that. I'd rewrite these two as the log of x to the 1/3 times y squared. And then I bring down the minus log of z cubed. But now I have the difference of two logs. And remember, when you have the difference of two logs, you can write that as the log of a quotient. So I write that as the log of a quotient where the numerator is the first argument, x to the 1/3 y squared, and the denominator of the argument is the second argument, z cubed. And so now I've wrote that as a single log. Now, the last thing I want to talk about is if you want to evaluate a log of some strange base, you can actually convert it to a log of any base you like. So the log of x base a actually is the same as log of x base b over log of a base b, where b is any base you choose. Well, so that means if I had log of 50 base 7, I could write that as log of 50 base 3 over log of 7 base 3. Or I could write that as log of 50 base 5 over log of 7 base 5. Or I could write that as log of 50 base 15 over log of 7 base 15. But none of these help me on a calculator. What I would really want to do, if I wanted to figure this out, I'd want to use logs that my calculator can calculate. So really, let's use base e log or base 10 log. So if I want to write log of 50 base 7, let's write it as natural log of 50 over natural log of 7, or common log of 50 over common log of 7, and then we can plug that in our calculator to get the answer. Here's just another example. If I want the log of 26 base 3, I just take the natural log of 26 over the natural log of 3, or I can take the common log of 26 divided by the common log of 3 and get the answer, 2.966. Okay, this last example, log of 5 base b equals 2.236. Log of 2 base b is 1.547. And it says find log of 50. Well, the concept here is to use log properties and see if there's some way that you can write the log of 50 as a combination of 5 and 2. And because if you can, then you can use this information to solve it, to solve log of 50. Well, here's what I'm going to do. Log of 50 base b can be written as log of 25 times 2. But log of 25 can be written as 5 squared. So instead of log of 25 times 2, I can write that as log of 5 squared times 2. Well, then I can use log properties, because this is the log of a product, and I can write this as the log of the first factor plus the log of the second factor. And then since this is a power, I can use my power property and move the 2 on the outside here and write that as 2 log of 5 base b. Well, now I know log of 5 base b is 2.236. I know log of 2 base b is 1.547, so I can just plug that information in and get 2 times 2.236 plus 1.547 and get 6.019. And again, that's just a little bit of a practice. All right, real quick, let's go take a quick peek here. Let's suppose we needed to solve 2 to the x equal 100. Well, we know 2 to the 5th is 64, 2 to the 7th is 128. So the answer must be between, actually I should say 2 to the 6th. So 2 to the 6th is 64, 2 to the 7th is 128. So the answer must be between 6 and 7. So how can we get a more accurate answer? Well, 2 to the x would equal 100 is the same as saying x equals the log of 100 base 2. Well, if I wanted to, I could write log of 100 base 2 as log of a common log of 100 over the common log of 2, and then that would give me 6.644. And you can check it if you like, but you'll find that 2 raised to the 6.644 is approximately 100. And in the next section, we'll talk about solving equations.